Chapter 2 is all about reasoning and proofs. In English, we use the word reasoning to talk about our evidence that we use to make an argument. And that's very much the same here. So there are two types of reasoning, inductive and deductive. Section 2.1 focuses on inductive reasoning. That is when we observe data, we look for patterns, and then we use those patterns to make some generalized statements, which we call a conjecture. So a conjecture is any unproven statement that is based on observations. So it is the result of what we do in inductive reasoning. So now we're going to look at some sequences of numbers, and we're going to predict the next two terms. So there's actually a typo in this one. That should be 1 for 16 and 64. And so now what we're going to do is we're going to look at the sequence and see if we can figure out some sort of pattern from one number to the next. So from 1 to 4, well, I've added 3, I've multiplied by 4, and that's probably the only two things I could have done. So now let's look and see what we've done to go from 4 to 16. Well, this time I've added 12, but I've also multiplied by 4. From 16 to 64, I've added 48, but now I've also multiplied by 4. So the pattern that's the same is I am multiplying by 4. So to predict the next two terms, I would multiply 64 by 4, which is 256. And then the next one is 256 times 4, which equals 1,024. In our next example, we're going to look at what happens in this sequence. Here, I've added 3, and then I've added 6, and then I've added 9. So now we know our pattern involves adding, and in this case we're adding multiples of 3. So to get the next term, we're going to add the next multiple of 3, which would be 12, and the one after that we will add 15. So the last term in the sequence right now is 13 plus 12 equals 25, and then we're going to use that to add 15 to get 40. In C, now we are decreasing our number, so in this case we subtracted 2, and then we subtracted 3, and then minus 4. So our operation is we are subtracting, and the number I'm subtracting is going up by 1 every time. So we could say subtracting consecutive numbers. So my next one would be subtracting 5 and then subtracting 6. So 8 minus 5 equals 3, and 3 minus 6 equals negative 3. In example D, in each case, this is a little bit easier to see when we have fractions, we have divided by 3. So I could say we are dividing by 3, but dividing by a number is the same as multiplying by its reciprocal. And sometimes when we have fractions, that might be easier. So we could say multiplying by 1/3. So in this case, so each time I'm going to multiply by 1/3. And so 16 over 9 times 1/3, the numerator stays 16, and the denominator becomes 27. And then the next one is going to be times 1/3 again, and so then the next one is 16 over 3 times 27 is 81. In E, we're no longer looking at a sequence of numbers, we're now looking at a sequence of figures. So in this case, our descriptions are going to be a little more varied from person to person. So you could describe this as adding in a vertical column to the left that is 1 block higher than the previous one. You could add 1 block to each column, and then add an extra one on the edge. Okay, so however you describe this is up to you. I like the description of adding one column to the left, one block higher than the previous. You could say taller, that works as well. So, if I was going to draw this, okay, I would have, the next one would be 4 tall for my first one, and then we complete the stair steps. And the next one would be 5 blocks tall. And sorry, this is definitely not to scale. But those would be our next 2 figures. Now we're going to look at another sort of way we can make a conjecture. So we're still going to be looking for patterns, but now our sequence is going to be built based on some sort of operation. So in this case, we're looking at the sum of the first n odd positive integers. So 1, 3, 5, 7, 9, etc. So, and we're going to want to come up with some sort of expression, and that will be our conjecture. So, first of all, we're going to start by creating our sequence that we're going to use to find the pattern. So, the first odd positive integer is 1. So, that's just itself. Okay, 1 plus 3 is 4. 1 plus 3 plus 5 is 9. And then an extra 7 is 16. Personally, I find it helpful to make a table. So if we put n in one column and we can just call it the sum in the other one, when n equaled 1, my sum was 1. When n was 2, the sum was 4. When n was 3, the sum was 9. And when n was 4, the sum was 16. So now we're going to look for a pattern that gets us from the first column to the second column. So it's a little bit easier to see what's happening. You could think of this like a function. So in this case, to go from n to the sum, what I've done is I've squared the value. So I would write that expression as n squared. And so when I make my prediction for the sum of the first 20 odd positive integers, I plug 20 in for n, and I square it. So my prediction is that they add up to be 400. Now, a conjecture was an unproven statement. So the next thing we're going to do is want to determine if it's true or false. To prove it's true, we're going to have to do a mathematical proof. So that's going to require that we prove it is true in all cases. And so that's going to be deductive reasoning that we'll get to in a further section. To prove the conjecture is false, all you have to do is provide a single counterexample. A counterexample is a specific example, and I only need one, that it shows that a conjecture is false. So what you're doing is finding the case where the conjecture doesn't work. So, for example, Mrs. Jones is looking at her class roster for first period, and she sees all her students in geometry that class period are sophomores. Based on that pattern that she observes, she concludes that all students in geometry are sophomores. How could you prove that her conjecture is false? Well, all you have to do is get the rosters for all of the geometry sections and find a single freshman on the roster in another section. For example, Miss Cardinal's first period geometry has several freshmen. Our next conjecture is the sum of any two numbers is always greater than the larger number. So this doesn't specify what kind of number I have to use. So let's see. What sort of number, when I add it, actually makes something smaller? Well, I can add a negative number. So let's pick 4, and then I'm going to add negative 2. So when I add those up, 4 plus a negative 2 is positive 2, which is not greater than the larger number, which is 4. So I now have a counterexample. I only have to provide one, but in case a negative number didn't come to mind, maybe you thought of adding 0, because 0 is still a number. So if I picked 5 plus 0, that equals 5. And since my conjecture is that it's always greater when I add them together, equal to is not part of that sentence, so I've also now just provided a counterexample that would also work. The next example does split between this page and the next, so we'll talk about the first line here, and then I will copy it onto the next page for you. So we're going to try to complete the following conjecture, which means that we're going to put an expression into this blank here, and we're going to be finishing the statement, the sum of any 3 consecutive numbers is some expression. Okay, so now I've copied that first line onto what in your packet is the third page. And so that one said 3 plus 4 plus 5 equals 12, which you can also write as 3 times 4. Okay, so now we have 5 plus 6 plus 7, which adds up to be 18. Okay, and we'll come back to that next line here in a second. So let's look at another 3 consecutive numbers. 7 plus 8 plus 9 is 24, which you can also write as 3 times 8. All right, so, all of these have a 3 in them, but they're also all even at the moment. So let's maybe, before we come up with a pattern, let's see if we can find any that add up to be an odd number. So let's try 4 plus 5 plus 6. Well, that adds up to 15, which is an odd number, but I can also rewrite that as the product of 3 times something. Okay, in this case it is 3 times 5. Here, this is 3 times 6. So we start to see the pattern that the sum adds up to be 3 times, let's see, here 5 shows up in the middle, 4 shows up in the middle, and that pattern continues on. So we're going to say it is 3 times the middle number. So here is your food for thought prior to our next lecture. Can you think of any counterexamples to the conjecture that we gave right here? Good luck!